Okay, good afternoon, everybody. Welcome to another wonderful day of operating systems. So today, talking about memory allocation at a fairly high level, and we'll go over some things that you probably shouldn't do, and some kind of fun new advancements in compilers to try and save you from yourself, and we will work around their help and try and crash it anyways. So, you've been doing memory allocation. You theoretically learned it in first year. Some of you are better at it than others. So there's a few different ways to allocate memory, and we went over a few of them. A few is, like the simplest one is called static allocation, which is basically just global variables. So global variables exist for the duration of your process. When your process ends, they end because everything is now destroyed. So this is all fixed size allocation. So if you have a global variable called char buffer and you give it the size of a page, well, that variable called buffer is going to last as long as your program lasts, as long as you put in global scope. So that's part of what the kernel in your compiler does. It will make sure that as part of the program, whenever it loads it into memory before it starts executing anything, it will make sure to set aside some virtual memory for that buffer and then give you the address so you can actually use it. So again, with this, all the memory exists for as long as your process lasts. There's no need to free it because the free is exit. So everyone is good with this. Everyone understands this. So good old global variables, thumbs up. No need to free, so they are perfect. But often you actually need dynamic allocation because the problem with static is, well, you have to declare everything up front. So you might not know how much memory your process even uses ahead of time. Sometimes they'll only use it in some certain conditions, in which case, if half the time your program uses next to no memory and in 1% of cases it uses 2 gigabytes, well, you're going to have to set aside 2 gigabytes of memory, which is of course going to be wasteful. So some other conditions that you might want to do dynamic allocation is if you don't know the size of anything. So with static allocation, I have to declare the sizes up top or up front. The compiler is going to know some of them, like how big an int is, how big a long is, how big a bool is, or whatever. But for arrays, you're not going to know the size of the array, and it can't give you memory up front if you don't actually know the exact size of that array. So if we do dynamic allocation, we have 2 options available, and hopefully we know them. So we can either do it on the stack or on the heap. And the stack is where local variables exist, and when you're outside of the scope of a function, then they no longer exist. So like stack allocation, that's done for you in C. So if I just have a normal variable in a function like int x, well, what your compiler will actually do is set aside memory for you on the stack. And there's actually, we've all used Malloc before, hopefully. So there's actually a way to ask the compiler or to ask for memory from the stack, which you've probably never used before because it's done for you. So the actual function call to allocate memory on the stack is called alloc_a, and it's like Malloc. You say how many bytes you want, and then it just gives you a pointer back. So C, most of the reason people use C is because C kind of does this automatically for you and saves you the headache. If you had to do this every time you declared a local variable, you would probably go crazy in like not very long. So as bad as you think C is, it's actually worse depending on what you use. So the rule for alloc_a is there's no free with it. And the rule is whenever that function that called alloc_a returns, it frees all the memory. And all it does to do that is it just restores the pointer back to its original position so it can reuse that memory. So no matter how many bytes you allocate, freeing all the memory is just done in one operation. It just moves the pointer back up to the beginning, you reuse the memory, and we all good. And the thing about this is that you have to be careful not to shoot yourself in the foot, because this won't work if you try to use the memory after returning. So let's see a little fun example here and see how we can break it. So here's our small little program. I can make it bigger. So we have main, it calls foo, and foo gives us back a pointer to an int. So we're just going to print out whatever that pointer is. And within foo, we will create an x, which should be allocated on the stack. We will set its value to 1. We'll print out the address of x, and we will return the address of x. So at the point of foo being done, x should no longer exist. But since we return an address, we still have its address outside of here, which if foo returns, it should be dead. So this should be an error. And this is actually a fun new advancement in the compiler, because this is actually undefined behavior. So you would expect here that whatever the address is here is the same here, right? Like address of x should be the same as p if I run it, right? So this is a fun new advancement. We'll compile it. It actually gives us a warning if we are paying attention, where function returns address of a local variable. And you're like, oh, warnings are fine, compiled. So let's go ahead and run it. So if I run it, I can see that my compiler is actually smarter than me. So even though they should be both the same value, because it's undefined behavior, well, C is allowed to do whatever the hell it wants to. And in the last year, they have recently decided that they will set it to 0. So if you try and use it immediately, and if I tried to like uncomment this line where I try and get, whoops. If I try and uncomment this line where I try and read its value, well, before it would just read some garbage value, and now it's going to segfault because it's null. If I dereference the null pointer, won't work. So that's kind of cool. Yep.
So are we trying to print the pointer or the value the pointer points to?
So this right now that I have uncommented prints the pointer. So this will print the pointer, and this also prints the pointer. So I should be printing exactly what I got, but the compiler is like, hey, you're doing something stupid, so I will set it to null. So if you try and use it, you won't get weird behavior. You will just segfault, which is probably a better option. But unbeknownst to the compiler, my background's in compilers, so there's an easy workaround for this. So it won't let you return the address of a local variable directly, but I can do something like int pointer to x equals the address of x, and then I'll just return the pointer of x. So now, hey, I'm not returning the address of a local variable directly, and my compiler's not that smart. So I can actually just use it now. And if I go ahead and run it, hey, they're the same now. So you can actually outsmart your compiler by not doing very much work. And it's still undefined behavior because, you know, you're returning the address of a local variable, but if you do it in a roundabout way, you can avoid all that overhead. So now I can uncomment this since I actually have a pointer. So here I set the value to 1, so you would think that, hey, if I read the value of it, well, should still be 1. Well, let's go ahead and see if that's true. So who here thinks it's going to be 1 still? We got hand wavy. So it could be 1. Could be 1, very definite 1. 43,000, and we can run this a few times. 43,000 went up by 1. It seems to be kind of consistent now. So the reason that it's just some more or less random variable is because, well, we return some memory from the stack, and then after foo returns, it's freed, so it can be used for anything else. And that anything else, well, printf needs the stack because it would have some local variables and stuff. So it would just set to some value it uses, and then we're just printing out something that actually printf is using now because it should be freed. So any questions about that fun stuff? This can be a fun source of errors. Yeah?
If you used it like right after you returned, would it still be the same value? Like it should be, right? As long as nothing else uses the stack.
Yeah, so we can see. So let's see. If nothing else uses the stack and we pray that it's still the value 1. So if we do this, it should still be 1. So let's see. So yeah, so this is 1. So this is a case where you're technically using undefined behavior, but after you return from foo, we don't create anything else, so we're good. So we could copy the value, and this works sometimes, but it's not guaranteed to work. Yeah.
Sorry, what was the problem with the thing before? Like how you said the stack was being used immediately after. So what was the case there?
So in this case, before I copy the value, because it's just pointing to somewhere in the stack, so the stack, it would be freed after foo, and that variable is probably not going to be touched whenever it just moves the pointer back and reuses the space. So it's set aside to be used for something else, but nothing else has used it yet, so I can go ahead and use it. So this is a fun source of bugs, because if you have something like this in your program, this will probably always work, but it's technically undefined behavior, and it will actually break because, I mean, we can just break it if we just go back. So now because it's undefined behavior, and this is like a new compiler thing in the last year, well, now if I do that, seg faults. So I don't get 1 anymore because it's smarter than me. It returned null, and I can't dereference null, so I can't try and use it or save it or do anything. So this is probably, yeah, so this is a fun new compiler thing that will probably cause some undergrad things to break eventually. So that was just a little fun demonstration. So any questions about that? That was more of a fun aside of the stack. All right, so let's get back into the actual content. So for other dynamic memory where you can't use a stack, so you might need to use other dynamic allocation, and that's the Malloc family of functions. So that's like Malloc, calloc, ralloc. I think that's most of them. And that's the most flexible way to use memory, but it's the most difficult to get right because you have to handle the lifetime of the memory and make sure you free exactly once. So as long as that memory I need lasts as long as a function lasts, well then a stack is appropriate. It's really fast to free. But if I want, for example, if I actually want to return a pointer to an int there and I wanted it to outlast the function, well, I suddenly can't use the stack anymore and I have to use something like malloc. So the deal with malloc is you're allowed to get memory back however many bytes you want, but the compiler is not going to know when you're done with it, so you have to tell it you are done with memory, and you have to explicitly call free, and that gives us all our fun memory bugs we all know and love, like you can't call free twice, you shouldn't use memory after you free it, which is more or less that same problem with the stack, so that's kind of the same thing as using memory after we free it. And also there is a new concern. We have fragmentation. So we saw fragmentation in the file system context before, where we had wasted space, so we didn't use all of our block. Well, if you're doing a general memory allocator, which we don't have to write a memory allocator in this course, you'll probably write it in a next course, but we can talk about and like the big general overall algorithms they use. So fragmentation is only a unique issue for dynamic allocation. So you allocate memory, they're differently sized contiguous blocks, and some things we can't do. Well, you could eliminate fragmentation if you asked for, if you asked for memory, you freed something in the middle. Well, if you wanted to make sure you don't have any wasted space, you could move all the memory together to make sure everything is contiguous. And that is basically what Java does. So as part of Java running and its whole heavy virtual machine, it will try and do this to eliminate fragmentation. But in C, you don't have that luxury because C isn't allowed to change the address for you. So if Malloc returns you an address and it's not allowed to change or relocate the memory whatsoever, so C's not going to be able to relocate anything because the decision is essentially permanent. So a fragment is just essentially wasted space, so it's a small contiguous block of memory that essentially can't handle any allocations. You can think of it as just some wasted space in memory. It's not useful anymore. Or you can think about it in the file system sense where I'm not using a whole block, I'm only using a bit of it, so I'm wasting a bunch of memory. So in order for you to have oh, sorry. Was that a question? Okay. What is it anyways?
It's kind of like, so you allocate something, then you would just allocate something on the next space on top of it, right? To be most efficient?
Yeah.
You allocate something on top of that?
Yep.
Is fragmentation just when something goes away?
Yeah. Yeah, so easy case for fragmentation, I could just allocate something else that, I don't know, is a different size, then allocate something else that is a different size, and then free the second one. So now there's a hole in between them, and now if all my other allocations are like too big to fill that hole, then that hole will never get filled and I can't do anything about it.
Like it'll never get filled? Couldn't you still maybe fill it in the future?
Yeah, well, I said assuming all the allocations are too big for it, yeah. But then there's a case where, oh, you might create other holes as you go on, even if you do find one that can fill it, and so on. So there's three main requirements for fragmentation, and they all have to be true. As long as one isn't true, you can avoid fragmentation. So first one is all the allocations have to have different lifetimes. So you can know this to be true. So for stack-based allocations, well, they're all different sizes, and you can't relocate anything, but the stack won't have any fragmentation because everything only lasts as long as a function lasts. So if you need 4 bytes, and then you need 8 bytes, and then you need 12 bytes, well, it'll just allocate them all nicely in a row because they last as long as the function, and then when the function's done, it just deallocates all of them. So it can space them right next to each other. There's no way to stop using a local variable, so I can't stop using one like halfway through the function. The next one is all the allocations have to be different sizes in order to get holes. So that you can think of as like our inode table. So our inode table wouldn't have any fragmentation in it because the inode table, everything is the same size, so everything's 128 bytes. So one block or one inode, space for an inode is as good as any other one. So you can always, as soon as you free it, you can always reuse the space. So no issue with fragmentation there because everything's the same size, so you don't have to worry about it. And then the third one is you can't relocate previously allocations. So if I could relocate something, again, I could just, what Java does essentially is like pause your program, move all the memory to be right close together, and that is why Java doesn't let you use pointers because it uses pointers that can change, so it's like a level of indirection. So you're not allowed to look at the pointers in Java because they might change under your feet when it actually moves the memory around. And it takes a lot of smart people to go ahead and figure out, oh, if I move the address of something, how do I fix up everything that refers to it? You could imagine trying to change the address of something in C when like 10 things refer to it, and you miss one, and you are screwed. So yeah, something like Java will do that, but something like C will not do that because all the decisions are essentially permanent. Okay, so, and there's also 2 types of fragmentation, so we can finally get into this. So there's external fragmentation that occurs when you allocate different size blocks. So that's within the like memory allocator to actually control, and there's no room to allocate between the blocks. So that's kind of what we've been talking about so far. And then internal fragmentation is if your allocator uses kind of blocks or some fixed size memory that doesn't exactly fit the allocation, well, then there's going to be wasted space in a block. So for example, for your file system, that has all sorts of internal fragmentation because it only deals with, in your case for lab 6, only deals with like a kilobyte block. So if anything is smaller than a kilobyte, any other space is wasted. So that would be internal fragmentation because your file system only keeps track of blocks of a size of kilobyte. It doesn't care about anything smaller. So that's also why your file system doesn't have any external fragmentation because it only cares about things being 1 kilobyte and that's it. It doesn't care about anything being different sizes. If anything needs to be bigger, it just breaks it up into fixed sizes of 1 kilobyte where it doesn't care. They're all treated equally. Okay, so if you're writing Malloc or you're just using your program, well, you want to minimize fragmentation because that's just wasted space that you should prevent. And there's lots of people that their full-time job is this. So like imagine Chrome developers or something like this, where they're wasting gigs and gigs of memory. And a lot of that is probably fragmentation. So they care so much about it that Chrome and most browsers will ship their own memory allocator to not use the same one you guys use because they know more specifically what they are doing and they don't want fragmentation whatsoever. So if you're writing your own like general purpose allocator, if you're writing your own Malloc, which we're not doing in this course, you may do later, you want to reduce essentially the number of holes in memory, and if you have holes, you want to keep them as large as possible. And the idea behind that is that, hey, if I have really large holes, I can actually use them for allocation, and therefore it's not really fragmentation. So your goal, if you're a memory allocator, is to keep allocating memory without wasting space. So allocator implementations usually use a free list. So we talked about a free list of pages. Well, that wasn't that general because pages are all the same size. And this is the more general one where we actually keep track of different sized memory allocations. So a general allocator will probably also have a free list and it keeps track of free blocks of memory by essentially chaining them together. And this is just one big linked list of free memory, and you also have to keep track of how many bytes are free. So if you're implementing Malloc, well, you have to be able to handle a request of any size. I can ask for 4 bytes, I can ask for 8 bytes, I can ask for 16,000 bytes, I can ask for weird numbers, I could ask for 7 bytes, and Malloc has to handle that. And then that's what you have to do if you're Malloc. And also, well, you have to implement free. So what free would do is add the block back to the free list. And if its neighbor, essentially, if its neighbor is also free, well, it could merge it back into one bigger block. So it can actually use that for a bigger allocation. So using that kind of general, really general free list, there's 3 general algorithms or allocation strategies you can do. There is best fit, so that's probably what everyone would think to do if they see, blocks of memory with holes in them and an allocation comes in and they have to do something with it. So best fit means it would choose the smallest block that can satisfy the request. Hopefully, it's kind of our goal we were thinking about before of maintaining large holes so we can actually use them for allocations. So this will use the smallest one possible and try and find an exact match. So worst case, it would have to search through everything in the free list, but in best case, if there's a exact match for the size of the allocation we need, it would just use that one and it can end early. All right, the next strategy is probably sounds stupid to you, and it is called worst fit, and it basically just does the complete opposite. So it just finds the largest block whatever has the most leftover space and uses that one. So it searches through the list, finds the biggest free block and says, yep, that's a good home for me, I will use that one. And then the last one, well, is essentially first fit, or essentially like, it's kind of like the FIFO idea where you just take the first thing that works. So as soon as I find a free space big enough for the request, I say, okay, I'm done, I'll use that one. So typically, whenever you first do memory allocators, you would use something like first fit because, well, you don't have to search through everything. But let's take a look at some examples to see what we have. So here's what I'm going to illustrate. So at the top there, that big bar is like how much memory the allocator is managing right now. And anything in a color is used, so I can't allocate in that space. And then any of the blank areas there are free, and they have a number associated with them, and that's how many bytes are free. So in this example, my memory allocator, at the certain point in the program, there's an allocation in red that I'm not allowed to touch. I have 100 bytes free, and then next I have some blue allocation, or teal, or aquamarine, I guess. Let's look at that color knowledge. And then we have 60 bytes free after that. So now if we have an allocation request, so someone calls Malloc 40, so we'll represent in green. Well, where should I place this block? So allocation for 40, which one should I use? Should I use the 100 space or use the 60 space? Yep. 60, yeah, 60, it's the smallest one. I'd want to leave that nice big 100 byte hole, so I'll go ahead and use the 60 space. So I put my green allocation there at the front or the back, whatever makes you feel good, and then I would have 20 bytes free now because 60 minus 40 is 20, so I have 20 bytes left over in my free list. So this is a bit hard to see, but now I have this purple block that is 60, so I should probably change the text color to white. So this is, so this allocation is 60. So now where can I put this block? Well, the 60 you can't see, doesn't fit in the 20, so I have to use the 100. So I'd put the 60 in the 100, and that also doesn't show up that well on the screen, so that's great. So after this, I placed the purple one, and now I have another allocation of 60 bytes. Well, my memory allocator in total, I have 60 bytes free. I have a 40 and a 20, but they're not contiguous, right? They're not beside each other, so it doesn't fit anywhere, and now I would just say, hey, I'm out of memory. Sorry. You actually have 60 bytes free, but I can't do anything for you. So that's not great. So let's see what happens when we do worst fit. So worst fit should be worse, but let's see. So if we're doing worst fit, we're going to do the same allocations. So we have the 40 byte in green that we can actually see. So worst fit, I'm not going to put in the 60 because my biggest block is 100. So I'll put it in the 100, and front or back doesn't matter. So I'd split that 100 block into 40 that I use, and then 60 is free. So now my memory allocator has two 60 byte regions left, and you can probably see where this is going. So my purple allocation is 60. Where do I allocate this? In this case, it doesn't matter because they're both size 60. So let's put it at the first one. And now I have my final allocation of size 60, and now it fits directly in my remaining space, so I can actually use all the memory. So in this case, worst fit actually worked out better for us, but nothing's ever really guaranteed. The thing about this is best fit and worst fit are both slow, and no one actually uses them to implement memory allocators because you have to search through the entire free list, which is going to be really, really slow. So what best fit does is it kind of tends to leave very large holes or very small holes, and the small holes are probably going to be completely useless. So they're going to be like a lot of really, really small fragmentation throughout the memory. And then if you simulate these things, well, if you do worst fit, simulation actually says that worst fit is actually the worst in terms of storage utilization, so it's actually a fairly fitting name. While the thing you actually implement if you simulate it is if you use first fit, which again doesn't have to search through the list, it just looks for the first free block that can fit, well, it actually tends to leave average size holes, which seem to work because you can actually reuse them for allocation. So it doesn't actually have that much, practical fragmentation, and actually works quite well. So, any questions about today? Sweet. Yeah, like I said, wrapping up on the course. So I'll probably just end early, and then we can ask lab 6 questions if we want to go over that. All right. So what we'll be doing tomorrow too. Well, the kernel actually has to implement its own memory allocations, because if you are the kernel, guess what? The standard C library doesn't exist. So you will not be able to allocate memory using Malloc, because if you are the kernel or the first thing booting, well, guess what? The C standard library doesn't exist, and the kernel's not going to use those types of memory allocators we looked at today. Those are like really, really standard allocators. We'll see what the kernel actually uses tomorrow. And the concepts are pretty much the same for user space allocation. So the memory allocators the kernel uses, you could actually use yourself. But what we'll see tomorrow is that they're not quite as general and have different trade-offs. But what we saw today, there are static and dynamic allocations. So static, global variables, you have to declare them up front. Dynamic, 2 types, stack and heap. Heap ones are through Malloc, stack are local variables. And for general dynamic allocations, like using Malloc and free, well, fragmentation is a really big concern. People implement their own memory allocators and really go out of their way to reduce that. And it's something that once you get into like high performance programming and really, really have to care about that stuff, well, it's going to be something unfortunately you have to care about, because that's a computer. So dynamic allocation, it will return you blocks of memory. The fragmentation between the blocks is called external fragmentation. Fragmentation within a block that the memory allocator is using is called internal fragmentation. And we saw 3 general allocations for different sized allocations. So worst fit, best fit, which again, have to search the entire list, and then first fit, which finds the first free block. So just remember, pulling for you, we're all in this